Okay. Yeah. So in the previous we talked about some basic field extension. So now we talk about the roots. So this section is the roots of polynomial. Also, just some simple results that you guys already knows. So define if p of x is some polynomial of coefficient f, and they says a. So there's a, right? So suppose a lying some extension field f. So basically, what I'm saying is that if you have a field extension k over f, which a belongs to k, such that p a is 0, then a is called roots. Yeah, so this is a very stupid idea, right? So everybody knows about. So for example, x squared minus 2 equals 0 has two roots, plus or minus square root of 2. Okay. Okay, and there's a remainder theorem. The remainder theorem tells you that if you have polynomial in f of x, in fx, then in the case is fixed notation, k is an extension over f. And for any b belongs to k, then you must have p of x equals to x minus b times p of x. Sorry, times some field has a polynomial and the r of x. So this is r of b. Okay, so what I'm saying is that we have p of x equals to x minus b q of x times r of b, and the degree of q will be degree of p minus 1, right? So this is also trivial, right? Because you can use a division algebra to divide x minus b to be q, and then you just put x equals to b will prove that this is r of b. Oh, so this is this is p of b. Yeah, p of b. Yeah, so you just put b, put x equals to b, so you get p of b equals to p of b. Okay, so this is the the simple result, right? This is so simple. Okay. Yeah, so let's talk about yeah. So there's a so now we have the corollary, but it has the important corollary. So the corollary tell you that if a belongs to k is a root of p in f, then so now yeah, then in kx, so in if you working in so now okay, so now your polynomial is in it, right? But in the extension field, if you have a roots in k, right, then you can in k of x, this p of x can be factored, right? So you can write p of x minus a times times something, right? So times some q of x. So what I'm saying is that x minus a will be p. Okay, will be this in kx. And so basically, what I'm saying is that in the extension field there is a factorization. Well, this is also simple, right? Because because you know p of a is 0, right? So by the remainder theorem, you just add p of a is 0, so you get this. Okay, so define the multiplicity. So if so a belongs to k has the multiplicity of m, means that x minus a and divides let's say this is p of x, right? So if a is a root of p of x, if it satisfies its m's power still divides m, but the x minus m plus 1 do not divide m. So this is called the multiplicity of the roots. Yeah, so this is simple, right? So let's say this just suppose your p of x looks like this, then the x equals to 2 has a multiplicity 2, x equals to 1 has multiplicity 1. Okay, so the next theorem. So this theorem says that a polynomial degree. So suppose you have polynomial p of x in f of x, and the degree of p is n. Then for any extension field, field K over F, P of X at most has n roots. Yeah, so this is also obviously, yeah, hopefully obvious to you that this is correct. But the proof is just make a just write down proof just the induction. So if your P of X to be, let's say ax plus b, right? Then you know that there's only one root, x equals minus b divided by a. Sure, a is non-zero. So that means degree p is correct. Degree 1, you have at most one roots, because now b and a are in F, right? So and the net roots must be in F, right? And you can use the induction, right? Suppose you have degree n, then you already find a roots, then you can divide that roots, right? You divide that roots, so remainder will be degree minus 1, and you use induction. Yeah, so the proof is I just saying. Okay, so now everything looks clearly. So up to now there's no yeah. So let me talk about example. So there's this is an example that the field assumption is important. So field is important. And so if you're working in a not field like quaternion algebra, means that you get this, right? So this is the quaternion algebra such that I squared j squared k squared is -1, and ij is k, and jk is I, ki is j, and then you change the order of these, then you will become there will be negative term, right? This is quaternion, and if we use, you can see that x squared plus 1 equals 0 has 3 roots, right? Basically, it's I, J, K. Okay. So that means the field assumption is very important. Yeah. So this is some counter example that you can try. Okay. So this theorem is important. So it says that if P is a polynomial in f of x with degree n greater or equal to 1 and irreducible over f. So I just learned that P of x is irreducible in f of x. So that means P of x cannot be factored in any kind of form in a field f of x. Okay, then you can find an extension E over f such that there's a roots E over f such that E. So such that the degree E over f is n, and P of x is a root. P of x has a root. Okay, so that means somebody give you any polynomial, right? You can always find another field such that that field has a root. Okay, so in that extension field, so this proof is a little bit tricky. Okay, so let's just tell you the result. So how to construct this E? Okay, so construct E is just using f, right? Using your original f of x and then modulo some maximum ideal, right? So and P of x is irreducible, right? So the natural maximum ideal is just P of x. Okay, and you can construct let's construct a homomorphism from field homomorphism from f of x map to. Okay, so maybe let's see. Yeah, I can construct a. Yeah, so there's now you have the natural map from f of x map to f of x modulo this p. Okay, and let's see. Yeah, so we already know this is field, right? So we need to show that this is the E is an extension over F. But this is not obvious. So let's define. So let's psi define to be this, right? So this is psi any f of x is basically mapped to map to the same thing, right? But just quotient p, right? So this is just the surjective map, okay? Or basically just map to f of x plus an ideal of D, right? So any element in this is just f plus this ideal generated by p. Yeah, so let me just using v, okay. Okay, so So now we have this yeah, so we have this one. Okay, so E will be this. Okay, so we now prove that the E is a finite extension over F with degree n. Okay, so obviously that this is intuitive because V is generated by P of X and P of X has degree n, and then there's no irreducible. Yes, this is irreducible, right? So somehow like in E f of X, right? When you collect all the when you construct X and X squared up to Xn power, right? Up to the nth power, you need to you can replace Xn to the power to be the rest. Right, so somehow like obviously this is degree n. Okay, so the proof is that in this element you can construct 1 plus v, x plus v, x squared plus v, right? This is the element representation, right? So you get the I, you get the xi plus v. It's a basis, right? It's a basis. Because up to n, right? You can replace it. So up to x plus v to n, you get xn plus v. And you can replace this xn to be the rest of polynomial, right? So now at most you have n basis. Okay, and the v is irreducible, so there's no further deduction. Yeah, so that's it. Yeah, so now is okay. So finally, I think finally we still need to show why there is a field, why there is a roots in this field. Okay, but obviously that so now we are working P of X, right? P of X should be fit into the should be the polynomial in sorry. So we need to ask why there's a root in E, right? Such that let's say this root is C, okay, such that P of C is 0, right? So we need to take the element, right? But by definition, this element can be choose to be X, right? Choose to be X, because the ideal germ, right? V is 0. So because this E, right? This E is this, right? So so if you pick up X, right? If you pick up X, right? You pick up X in E, then by definition P of X is 0, right? Right. So this X is a root in it. So basically this. So this is a little bit abstract. So example is that if you're working x squared in 0 minus 2 in Q of Q, right? There is no field, right? No roots, right? But actually it has a roots, right? BA has a roots in Q, the adjoint square root of 2. Then you are saying, oh, I define square root of 2 in this manner such that the square root of square minus 2 is 0, right? But what I'm saying is that you can define Q square root of 2 as a Q of X modulo X squared minus 2, right? Then this X will be a root, right? So this is the extension over Q, right? So if you have this, and then you can say that Q of 3 square root of 2 is isomorphic to Q of X modulo X through Q minus 2, right? So this X is a root, right? So it looks stupid that you just quotient this, right? But actually this is the whole technique. Okay, so another theorem. This theorem says that if you have a polynomial fx, and then there is a finite extension over E. So if you have this and there is a finite extension over E, such that fx has a root, then what? Then obviously that E cannot be too small, right? Because you already have a root, okay? So E cannot be too small. So actually E cannot be too large. It don't have to be how should I say? So I mean, I should say, sorry. If f of x belongs to a polynomial, and And okay, so now this is a consequence. There is a extension. Okay, so what I'm saying is that if you know your polynomial f has degree n, and then you can prove that there must exist some field extension E over f, such that f of x has a root, then E over f can be less than n. Okay, so this is the trivial, right? Because I already showed that you can construct E equals to fx modulo v, right? Modulo v. So which tell you that in E, you already have a root. So other field which has a root can be less or equal to n. Because I already showed that you must have you can construct an extension field E over f is n, such that there's a root, right? So there may be other choice which in other field there's a root, right? So I can construct this. Yeah, so this is just logic. Okay. Okay, so find this now. This is the important theorem that I think is interesting. So after this theorem, then we can finish this section, and then we will talk the rest in the next video. So if you have a polynomial and the degree of f is n, then either an extension field such that all roots. Okay, so I should say n roots. So E has n roots. So E has n roots is the same as E has all roots, right? Because the polynomial with degree n has at most n roots in any extension field. So E has n roots of f of x. Then, so I mean, there's a exist E, right? So I say there exists E, and I say that E, the dimension can be chosen to be not so large. So E over f at most n factorial. Okay. So I hope you guys understand what I'm saying about. So what I'm saying is that if you have degree n polynomial in coefficient f, then you can find an extension field E. Then this E has n roots of f of x, then the E has such that so I can find the E extension of f such that E has n roots of f, and E over f can be less or equal to n factorial. So that means that the complexity is the complexity of the roots is be constrained by a degree, right? By degree. Okay. Oh, so I should maybe I use oh shit. And right, and this. Okay, so the proof I want to use is the just the induction. So by previous result that I know that the E0, I know that you can find if there's a root, right? If there's a root, then E over f is less or equal to n, right? So that means I can first find the extension field E0. Okay, such that f of x has a root. I say has a root, not necessarily has only one root. Maybe it has n roots, right? So that means I can find such that E0 over f is just n, less or equal to n, right? But now since you already have the roots, right? So I can so I can write f of x can be further degree to f1 of x, which degree of f1 is less or equal to degree f of f, degree f minus 1, right? Because there may be multiple roots already shown is E0, right? Then you can do the second step such that you can construct another E1, right, over E0, such that the rest of f1, such that the rest of f1 has a root, right? This will be degree n minus 1. Then you keep going, right? But finally you will end it. So and you use the formula that E over f. Okay, so finally the final step is E, right? So it can be written as E n minus 1, E n minus 1, E n minus 2. Keep going, then finally you get the 1 to up to n, right? So this is less or equal to so n factorial. Okay, so that means if you have a degree 3 polynomial, you at least you can find the extension field at most the 6, at most has the degree over 6, which can eat all these roots. Yeah, so this is I think the beautiful results. Okay. Okay, and then next time we can talk about the splitting field. Okay, so I think up to now we already know this some basic of the polynomial ring. I think this is easy, right? I mean the roots in the polynomial, and the astonishing results is this one, right? So the first one is that any if you have a polynomial irreducible in F, then you will always find a field extension such that there is a root. Okay, so but once you have this, then you can also show that this extension can be choose their degree can be choose not so big. Then once you do this, you can generalize into that if you must contain a root, then your extension can still not be so big. You can choose like n factorial. Yeah, so this is the interesting consequence. I mean, because my English is not so well, right? So, but hope you guys can understand. See you guys next videos.